So now we are mentioning a specific tool here, general equilibrium model, which I mentioned before as well. I can't remember if I really defined it. I'm not going to define it in great detail either way. Basically, these general equilibrium models evolved. Obviously, they're economic models. They evolved, I think, as far back as 1950s or maybe earlier. You can look up. But essentially, they take all the economic variables, the system, and try to look at how it responds to perturbations like change in policies or technology or some other perturbation, maybe even the pandemic and so on. We will read a bit more about these models, econometric models, in the annex at the end of the main text here. So here we are looking at general equilibrium models of adaptation to analyze growth debt trade-offs. So it's not just the economic model, it's a general equilibrium model of adaptation. So general equilibrium models are useful to determine whether development plans, including adaptation and financing strategies, are coherent. Investments in adaptation deliver benefits, but they can be costly. Upfront costs can be very high. Future benefits are always discounted. In particular, costly investment in resilience puts strain on public budgets but shores up growth when natural disasters occur. May happen very quickly after the investment or may not happen for a long time. So who pays for it may depend on the memory of the investment when disaster happens. Therefore, general equilibrium models can be useful to assess whether specific adaptation strategies are sustainable under a plausible calibration of key economic relationships and climate shock realizations. You plan for a shock. When does it actually happen? That is important. GE models can also be used to compare the costs and benefits of reform packages. Reforms aimed at protecting the economy from climate risks can be combined and supported by supplementary measures. The success of protection strategies can hinge on these supplementary reforms, whose effects are best illustrated with the GE model simulations like those generated by the IMF DIGNAD model, which is one of the GE models. We'll briefly touch on it in Annex 1. For example, improvements in public finance management can be instrumental for the development and implementation of adaptation investment plans to deliver on expected returns. Lowering borrowing costs by mobilizing concessional financing from development partners or domestic revenues can help to safeguard debt sustainability despite costly adaptation measures. Alternatively, simulations can be used to determine the magnitude of reforms needed to ensure adaptation plans are sustainable. I'm reading this text here because this is a place where my intrinsic depth of knowledge is not that great, so I'll just try to make sure I don't miss any points. Implications of climate uncertainty for physical protection and insurance policy options need to be analyzed by running a large number of shock scenarios. So you are underwriting risks with tools like insurance, and there is climate uncertainty itself when you plan for physical protection as well. So then they need to be analyzed using a large number of shock scenarios, and the shocks are not stationary. So we talked about return periods which may increase, which may decrease from 100 years to 50 years and so on. This approach can be implemented by repeating simulations of deterministic models used on different random climate shocks and by stochastic models. So deterministic models are basically things that give you a number as opposed to a storyline, let's say. Such an approach can also encompass dynamic stochastic general equilibrium models, which we will read in a minute. Okay. That can explicitly incorporate the distributions of climate shocks. It's not just a national level thing, but how multiple shocks can be distributed in space and time. This approach improves on dynamic general equilibrium models that are limited to the study of a few specific disaster shock scenarios. Okay, so there are details there that, as I said, I don't have a very intuitive sense for, so I'm just translating as best as I can, and you need to go up and read up and follow up with the details if you are interested in this. The DSGE model, dynamic stochastic general equilibrium model. Stochastic refers to randomness, and dynamic refers to capturing these kind of perturbations. DSGE models can be used to analyze the long-term implications of climate shocks and shifts in their distribution on investment. So we're always coming back to investment. Recent developments in structural modeling provide a way to evaluate how the distribution of climate shocks affects macroeconomic outcomes at the large scale. So how money flow and other things happen, and not, firm scale economics and so on. For example, this paper in 2019 assumes that agents' expectations about weather-related disaster shocks affect the stochastic steady state of their model, and find that the higher expected frequency of natural disasters hinders private investment spending even in the absence of an actual disaster realization, as the return on investment is expected to be lower and thereby contribute to aggravate the effect of climate change on GDP. In a slightly different context, but I commented in an article elsewhere that I wrote in the media, that articles that said something like the heat wave in Uttar Pradesh in June in India was more than doubled in terms of its probability because of global warming, can have these sorts of impacts, where how do you interpret that the probability was doubled? This is a weather event. Does this mean all events will be doubled in frequency or probability, or is it that this particular one happened and it doesn't have any bearing on the future? Well, how does it affect the perception of the investors or the investment the government has to make, either it's central government helping the state or the state trying to deal with this shock? So these dynamic stochastic models have to worry about such things. DSGE models, dynamic stochastic general equilibrium models, are useful to assess welfare trade-offs of climate change policies. We'll look at a box in a minute, so I won't go into the details. DSGE models can also quantify the effects of stochastic shocks and the expected cost benefit of adaptation policies that reduce risks, including insurance policy options. Here, for example, DSGE models can be used to calculate the probability that post-disaster financing needs would exceed a particular level in a given year or group of years under different insurance options. So standard commercial insurance contracts, self-insurance by accumulating savings, state contingent debt investments such as catastrophe bonds, and so on. Stochastic DSGE models have been coupled with deterministic models as opposed to stochastic to study near-term dynamics, to study, for example, impacts on income distribution. So there are many examples, lots of literature there, so all these papers that are cited here are useful if you want to follow up. So these GE models are also often now called computational GE models or applied GE models, because they use data to do their model simulations and so on. Okay, the wealth of information provided by DSGE models comes at a cost. For example, in addition to their stochastic capabilities, DSGE models can typically feature many sectors, including detailed energy sectors, and can be tailored to study distribution issues across heterogeneous agents. However, using, developing, or calibrating these models to new settings requires capacity and time, and often it needs lots of data. So if you are looking at an energy sector and trying to recalibrate it in a new setting for the same region, or trying to move it to another region, you will need a lot of historical data to develop some parameters, calibrate these, and validate them and assess them for the historic period before you start using it for future scenarios. DSGE results can also be very sensitive to model calibration and, as for other models, to the assumed probability distribution of climate variables, which is uncertain and changing. So you're taking, chronic or acute risks from climate projections of some sort, which have their own uncertainty, which is scale dependent, time dependent, because the Emission scenarios are given to the climate model, which projects future climate, which is good at certain things like temperature, and then not so good at, let's say, extreme rainfall, and is good for both only at a certain scale and not at a local scale. Then you are trying to translate those uncertainties, uncertain risks and projections into these DSGE models. So how you prepare the DSGE model itself can depend, its result simulations and projections may depend on the probability distribution of climate variables. So these are complicated issues. So let's come back and look at box 3 and then box 4. Timing is good because I'm getting a phone call, as you can hear it probably. So see you in the next podcast.